Picking back up with more on the groups or families on the periodic table. The next one is the transition metals. So these are all of the B families, all of the ones that are between the big columns on the periodic table. These are what we call the structural metals. So things like lead, copper, zinc, silver, gold. And the reason why these are our structural metals, the ones that we use for things like building, iron is in this group as well, because they have lower reactivity with water. So unlike the alkali metals and the alkaline earth metals, those guys do react with water. They like to react with it and bind with things like oxygen. These structural metals will react with water, but they have very little reactivity with water. So they work really well as building materials. They are also harder metals. So those alkali metals and alkali earth metals are very soft metals. Versus these guys, when they are, because they're usually in their own individual form, they may be bound in ores, so they might be reacted with something like oxygen. But when we extract them, when they're by themselves, they're generally fairly strong, hard metals compared to the other two metal groups. So it contains a lot of very well-known elements. So I've already listed a lot of them that belong to this group. There's a lot more. So if you take a look at the periodic table in those transition elements, you'll probably recognize a good chunk of the metals that are in there. Titanium is there as well. So we have a lot of these transition metals that we use in our everyday lives as well as in other pursuits. So then the right-hand side of the table, so we're just going to kind of go across those columns there. So like I said, 3A to 5A, they don't have any common family names. They don't have super high reactivity. And they have a mix of metal, non-metal, and metalloid. So that's part of why they don't have any families. They do have things in common, but they are not nearly as kind of similar for each column as we see with the other families, because you've got that mix of the three different types of materials in those columns. But you can see carbon belongs in that group in one of those three families. So then we've got 6A. So this is the Halogens. So these are the ore forming elements. These are fairly reactive. So they are commonly bound to other materials, hence ore forming. So this includes sulfur. Hence why we've got the picture of sulfur right here. This also includes oxygen. And I couldn't put it in a picture of oxygen since it is a clear gas, but oxygen belongs to this family as well. So you rarely find these guys as pure elements unless they are bound to themselves. And that's what you're seeing here. So you're seeing sulfur bound to itself. You can get oxygen gas, which is, bound to two oxygens bound together. Otherwise, they're going to be, because they're so reactive, they're going to be bound to other things like H2O or sulfates. So they are going to be reacted with other elements. We've got two more major families, the halogens. So this is 7A. These guys are Greek for salt forming. And that's because these are commonly found in salts. They're highly reactive, and we'll see in the next chapter why that is the case. But which one of these do you know from salts? So we've got the three best known of the halogens here. We saw this picture earlier. So we've got chlorine, bromine, and iodine. And so my guess is the chlorine is the one that you recognize. So chlorine makes sodium chloride, table salt. Bromine, you may have come across bromine if you've ever had a surgical procedure, because this is one of the disinfectants that we use. Iodine. Iodine you might recognize from salt as well, because we iodize salt because we need iodine in our diet. But all of these guys show up in salts because they bind with things like sodium and calcium very, very easily. All right, our last group is 8A, the noble gases. So this is the far right-hand column. And these guys are colorless, odorless gases. So can't really see them, smell them, anything. And they're unreactive gases. They tend not to combine with other elements unless they're forced to. And when I say forced to, we force them to do it, putting them under heat and pressure, or using some sort of catalyst, a chemical, to be able to make them react. Otherwise, they just want to be left alone. So why noble gases for their name? Because the other ones all, you know, they've got kind of bases for their name. Noble gases, the reason why they were named noble gases is because they're unreactive. And the nobles back in the time were people who didn't interact or react with the peasants, the lower classes. And so that's why they were given the noble gases, because they stay away from all of the other elements. Oh, and the other thing I wanted to point out before I went to the next group is you actually know the noble gases from neon signs. This group is one of the groups that gives neon signs their colors. There's some other elements that are used for it as well. And what's funny about the name neon sign, the only color that is actually made from neon is this kind of bright reddish orange color. All of the other colors, as you can see, we've got helium, argon, krypton, xenon, and then you can use other gases as well and other elements as well to create the other colors that we see in neon signs. And they work by exciting those electrons with energy to get them to release the photons that we talked about in a previous video. There's two other special groups. They're the lanthanides. These are sixth period rare elements. So this is the little strip of guys on the periodic table. So let me zip back to the periodic table. There it is. So you can see here, this one's marked here, the lanthanides. We're also going to talk about the actinides. So these guys actually do slip right in here in the middle of the transition elements, but these guys have a separate classification, and that is because of what they can do. So let me get back to their slide. These guys are called rare earth elements, which is interesting because they aren't earth. So like the other alkali earth elements, they are not non-metal or non-reactive, and they're not rare. The thing is with the lanthanides, they are similar to each other in physical and chemical characteristics. It's very difficult to actually tell these guys apart from each other. They are commonly also found mixed together, and makes it difficult for them to purify into the different elements. But these guys are incredibly, incredibly useful because we've been able to harness them to use in a lot of items. So you can see here, we use them in LED screens, optic fibers, laser crystals, magnets, electric motors, ceramic superconductors, heat-resistant engine parts. I mean, these elements are all over the place. And so if you're wondering about the magnets one, you may have one of the magnets that belongs to this group. They're neodymium magnets. They're some of the strongest magnets that we have today. So, you know, these elements are insanely useful. And so we've actually worked to separate them from the rocks that they're bound to, hence why we thought they were earth elements, and work to purify them into the individual elements since they're so incredibly useful. This is also why we are working to try and do some recycling of the materials that they're in, because it is expensive and difficult to get them out of their ores, their rocks that they're from. Like I said, they're not rare. Actually, the rarest of these is actually more common than silver. So yeah, they're not as rare as we once thought. The last group are the actinides. So this is the row underneath of them that's set out of the table. They have the same problem. The whole group of actinides have similar properties, are difficult to purify. So then the question for this group is, why would we want to, right? The lanthanides, you can see all of the uses that they have that we've been able to figure out for technology and so forth. The reason why for this group is there are nuclear elements down here, specifically uranium in the natural elements and plutonium in the man-made elements. We can use these guys to generate energy. And so we can use these in nuclear power plants to be able to make electricity. And so it's incredibly useful for us to be able to isolate these actinides. Any of the actinides heavier than uranium can only be created in labs. So those, the ones that are above that are going to only be created in labs. So plutonium and up, you're only going to be finding man-made versions of those. So let's take a look again at the periodic table to look at a few more characteristics. We've made it through all of the families. So let's take a look at some trends that are actually on the table. So we can see they're grouped by characteristic, right? So all of these guys, well, not hydrogen, but all the rest of them have stuff in common and so on. So we can also see that the periodic table is grouped by atom size. So the way it got laid out ended up generally the bigger atoms are on the left-hand side of the table and the smaller atoms are on the right-hand side of the table. And the biggest atoms are down towards the bottom of the table and the smaller atoms are up at the top of the table. And that makes sense because these guys are going to have fewer electrons, fewer protons than the atoms that are at the bottom. So let's see, the other one that I want to show you is tying us back to the shell model that was in the previous video. So I mentioned that the shell model is related to the periodic table. So here we've got our Bohr model, our shell model. And if we look, we're looking at just the first three periods, period 1, 2, and 3, the ones that are highlighted up here. And let's take a look at how their electrons are laid out. So the first period elements, it's just hydrogen and helium. Okay? And if we take a look, so hydrogen, a neutral hydrogen has 1 proton and 1 electron. And so that 1 electron goes in that first level. A neutral helium is going to have 2 protons and 2 electrons. And the maximum number that can go into shell 1, if you look back, is 2. So that gives us shell 1. Let's take a look at the second period. So we've got 2 shells now because the shell 1 is full because an element or an atom of lithium is going to have 3 protons and 3 electrons for a neutral atom. And because it's got an atomic number of 3. So if we start filling up the shells from the center out, we're going to put 2 in the first shell, and that leaves us 1. So we've got 1 shell with 1 electron. If we go across, we're going to see, well, this guy has got 2 because beryllium has an atomic number of 4. Boron has an atomic number of, I might be catching on, an atomic number of 5. So it puts 3 electrons in that second shell. Carbon has 6, 7, 8, 9, 10. And so by the time we make it over here to neon, we have 2 in shell 1, 8 in shell 2. And if you look back, the maximum number of electrons that can be in shell 2 is 8. And this is why neon is not reactive. It's not missing any electrons in this outer shell. In our next set of videos, we're going to talk about from the next chapter. These guys here are reactive. So oxygen and fluorine and beryllium and lithium are so reactive because they have these electrons just hanging out in that outer shell. There's not enough electrons. So we've got these guys with 2 shells, right? Second period. Take a look at what happens for third period. Sodium. Sodium has a atomic number of 11, 2, 10, 11. Third shell. Turns out the periodic table, when it got laid out, we didn't know about the Bohr model or shells, but it ended up getting laid out with shell 1, shell 2, shell 3, 4, 5, 6, 7. So all of the elements down here, if we count them up, including the actinides, there are 32 elements down here. Right? If you count across here, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements. Across here, there are 18. And so this periodic table got laid out, it turns out, based on the number of electrons and how they get organized in these shells. So, all right. So the next set of videos is going to talk about physical and chemical properties and how these atoms get bonded together.